Hey everyone, welcome to The Explainer. I am absolutely thrilled you're here today because we are tackling one of the most pressing challenges in the AI space right now, scaling multimodal workflows. Look, we've all watched multi-agent LLM systems evolve, right? They've gone from these isolated single-agent setups to highly complex, coordinated swarms, but the second we try pushing these systems to handle text, image, audio, and video all at the exact same time, we hit a massive wall. So today, we're going to unpack a brand new open-source framework that actually aims to solve this exact bottleneck. Let's explore how it works.
Okay, let's dive into this. Here is our roadmap for the explainer. We'll start with the orchestration bottleneck. Then enter Orchestra-o1. Look at the three core mechanisms, explore shattering the benchmarks, and wrap up with the developer playbook. I really want to start with this quote, directly from the source material, because it perfectly frames the hidden crisis we're facing today. The bottleneck is no longer base model capability. It is orchestration. Think about that for a second. Our base models, the underlying engines, are incredibly strong. The raw intelligence is totally there. But the coordination between them, it is totally fractured. When you try to get these brilliant models to collaborate across different types of data, the system bogs down. Not because the models aren't smart enough, but because they literally just don't know how to talk to each other efficiently.
Section 1. The orchestration bottleneck. Let's see why existing multimodal pipelines are fracturing.
And this brilliantly illustrates the problem. We have all these heterogeneous data streams flooding in. Text, image, audio, video, but current architectures try to handle it by forcing rigid, hard-coded modality switches. It basically creates a giant traffic jam, forcing data into a single file line. This gives you high latency, it rapidly exhausts your context window, and ultimately, it consumes 30 to 40% more tokens. It's incredibly wasteful. You're burning tokens just on redundant modality headers and context switching. By contrast, Orchestra-o1 utilizes parallel execution. It's inherently modality aware, and it keeps context windows cleanly isolated. So instead of a traffic jam, you've multiple perfectly synchronized superhighways.
Moving right along to Section 2. Enter Orchestra-o1, the Omnimodal paradigm shift.
So, this framework arrives as the hero solution, completely shifting routing away from those clumsy sequential tool calls. Let's formally define it. Orchestra-o1 is an open-source orchestration layer built specifically for Omnimodal environments that utilizes dynamic, parallel, modality-aware task decomposition. It's kind of like a symphony, right? If the old pipelines were a conductor forcing the brass, strings, and percussion to play one at a time, Orchestra-o1 is a master conductor perfectly timing every single section to play simultaneously. It reads a unified score to produce a cohesive output without anyone stepping on anyone else's toes.
Section 3. The three core mechanisms. Let's look at the anatomy of the engine.
Let's pop the hood, shall we? We're going to examine the three fundamental pillars that make this dynamic orchestration engine actually work. The first mechanism is modality-aware task decomposition. When raw, messy data hits the system, the orchestrator instantly parses it, finds the modality boundaries, and splits the inputs into discrete subtasks. By aligning specific inputs with specific processing units right at the gate, it prevents what we call cross-modal token pollution. It keeps the context windows perfectly focused on relevant data types rather than just jumbling text, audio, and visual tokens together in a confusing soup.
Now, what's really interesting about this next one is online sub-agent specialization. Instead of relying on pre-trained static routers that break the second a new format shows up, Orchestra-o1 actually configures its sub-agents during runtime. If a video feed comes in, boom, a vision sub-agent instantly spins up to handle frame extraction. At the exact same time, an audio sub-agent adapts to process the spectrograms. It all happens dynamically based on real-time inputs. For you, that means drastically less engineering overhead when new input formats inevitably pop up.
And the final pillar is parallel subtask execution. Those specialized subagents we were just talking about, they run concurrently as independent processing units. The orchestrator just monitors them and aggregates the results only when the cross-model dependencies resolve. This design scales horizontally beautifully. It aggressively reduces idle time and completely stops the context window exhaustion that you get from sequential token accumulation.
Section 4. Shattering the benchmarks. OmniGAIA dominance and DAGRPO.
Okay, theory is great, but we want to see the proof. Let's transition into the testing phase to see how effective this really is. 10.3%. I want you to let that number sink in. You know as well as I do, in the world of AI benchmarks, getting a 1 or 2% improvement is often celebrated as a major breakthrough. So 10.3% is absolutely massive.
On the OmniGAIA benchmark, Orchestra-o1 is sitting on a commanding 10.3% accuracy lead over the second-best approach available. And what does that lead come from? It comes directly from eliminating the waste of redundant modality headers and just dropping that heavy penalty of constant context switching you find in older pipelines.
Now, driving the 8 billion parameter variant of this system, Orchestra-o1-8B, is a training method called DAGRPO. That stands for Decision Aligned Group Relative Policy Optimization. What this does is optimize the model's policy updates based on agent decision trajectories. So the crucial point here is how it actually trains. When you rely on raw reward signals across heterogeneous modalities, they are heavily misaligned with actual reasoning steps. It causes a total nightmare of gradient instability and noise. DAGRPO, on the other hand, tracks decision boundaries across modalities. It aligns the optimization gradients with the actual task completion steps. This stabilizes training and ensures your updates reflect genuine capability gains.
To summarize the performance edge here, Orchestra-o1-8B hits state-of-the-art results across all existing open-source omnimodal agents, and the gap actually widens when you push it into complex cross-modal reasoning. Because it processes audio transcripts and visual frames simultaneously, it maintains strict temporal and spatial consistency, which is exactly what sequential pipelines inherently degrade and fail at.
Section 5. The Developer Playbook. Let's look at actionable next steps. I want to speak directly to the developers and engineers watching right now. How do you actually deploy these concepts? Well, here are your technical recommendations. First, evaluate your routing logic. If you are sequential, replace your static splitters with modality-aware decomposition ASAP. Second, parallel execution will introduce memory fragmentation, so proactively profile your GPU memory allocation. Third, pin your orchestration versions in your dependency manifests so you don't get breaks during sub-agent hot swaps. Fourth, log those state transitions and cross-modal dependency graphs to avoid gradient explosions. And finally, please implement fallback routing. Hard-coded modality assumptions will cause routing failures the minute inputs shift. You've got to be prepared for unrecognized formats.
To make this super clear, here is a quick 3-step implementation plan to ensure reproducible results and reduce token overhead. Step 1, evaluate your current routing logic and benchmark it against the OmniGAIA methodology. Step 2, measure your context window utilization pre- and post-migration so you can prove the actual reduction in token overhead. And Step 3, integrate DAG-GRPO if you are actively fine-tuning open-source vision language audio models for agentic workflows.
I'll leave you with this provocative question to ponder. Is your multi-agent system actually ready to orchestrate, or are you still waiting in a sequential line? The data is crystal clear, the architecture is open source, and the code and paper are up on archive right now. Go check out the repository, rethink those multimodal pipelines, and start building the future of AI swarms. Thanks so much for joining me on this explainer. Keep learning, and I'll catch you on the next one.